Hello everyone. So today we will begin with the new stuff, to build the new stuff. We will see the stochastic processes, martingales, which is a very important part, and if we have time, some frozen motion. We will see. I just have to recap what we saw last time. So we saw how to define a random variable, how to compute the expectation of something. So it's just the expectation is exactly an integral. It's the definition. It's integral with respect to the ambient probability measure. Okay, and we saw that we could write it with the law of x, and if x has a density, we can write it this way, which is a nice expression that we want to use. And one random variable that we will see all the time is this one, the normal Gaussian random variable with density, this thing. And again, you can check that it has, it's a probability measure, but the integral of this thing is 1. It's an exercise. It's actually not easy. Then we spoke about the probability, the convergences, and the different convergence and rules of convergence that we have for random variable. So we saw that the equivalent of what we use in the day-to-day real deterministic analysis is the almost sure convergence. Then we have convergence in empty spaces, we know, and we will have a weaker one that we call convergence in probability, which is much weaker. And we saw that the one that we really care for in probability is the convergence, where you see that xn tends to x if rho xn tends to rho x. That's what this one.
Yeah. Almost sure it's almost everywhere.
Yeah. It's a problem. It's for almost every omega, xn of omega tends to
with respect of p. Almost everywhere with respect of p.
Yes? Yeah.
Let me translate.
It's also the strongest one for us.
Okay. What is negative infinity once again? So the convergence in negative infinity, this is with respect of, this is also the measure space with the.
Yeah, I think that if you integrate this.
Yeah, supremum norm, or this is P norm. Okay, in LP, but you mean in supremum. Great. Then the lowest one, what is the
law?
No.
Oh,
So this is the distributed.
That's mystical.
It's mystical, but it's the best one. It means that if you take the measure that defines like this one, for instance, is the density, it means that mu xn tends to mu x. It's a convergence in measures.
Is the pullback measure?
Push
Push forward measure to do the state space.
Push forward to the space and the body map. Push forward.
Okay, you can see it.
So it should be continuous map from one measure space to another space. In one you have, of course, your measure.
It basically means that the expectation of a function that is smooth, bounded, evaluating an extent converges to this one.
And the extent is in your probability space.
Yeah, it's the random variable. It's a measurable function, basically.
And P, the last one, I'm sorry, where I'm from analysis. Then last conversion P.
Yeah,
the center.
This is converted to measure.
We'll not use it this week. It's a bit stronger. We'll recall the definitions when we need it. Because it's
That's what we call convergence in measure.
Yes.
Okay. It's just translation.
it's fine.
Almost everywhere, LP in measure and push forward measure.
And we will mostly use this one and this one just to define the stochastic.
Push forward.
Push forward.
Push forward when you have the measure space and another space, and you push it measure by recomposition with this method to happen. That's it.
So today, the point is to define and understand the key properties of what we call stochastic processes. I think I put the correct number of C from S's and that. All right. So we've talked a lot about random variables. That is, you have some probability space, omega, with your measurable set, so your events F, and your probability measure P. We want to introduce some notion where we have a random variable that changes with something we call time. So we want a changing random variable. So what I mean by this is that we'd like to have some sort of index space, right? Call this index space time. And we want to imagine that as time proceeds forward, that this random variable is somehow changing with respect to that. So in addition to this probability space, we introduce T. It's a measure space or measurable space. Change, which call. All right, so we have some measurable space T with a sigma algebra tau, cursor T. Let's make it cursor T. It's probably better. Now, in general, we've really only got 2, maybe 3 cases. So almost always, most often, T is either R. We can say RT. With Borel sigma algebra. It's also often, what am I doing? I apologize. I'm getting ahead of myself. The non-negative real numbers, this is what I would like for. Or some finite interval that we often, by use of notation, write T in here. Or we will take the natural numbers. These are the 3 that you see most often. So in these first 2 cases, we're using the Borel sigma algebras, restricted to them. And here, we take the power size. Any so in these first 2 cases, in this continuous situation, when T is n, we'll call this discrete. And what we then say is that x map from omega cross T, whatever index space is, into S. S and some measurable sets on S. So we can have left for this. Yeah. So this be a random variable for each fixed T. Okay. So what am I saying? I'm saying we now have 3 measurable spaces. We have omega FP, which is actually our probability space, as we've been talking about last week. We have T tau, which is somehow measuring time, and it's almost always going to be either some, some version of the real line. want me to do the filtrations later.
Okay.
Yeah, you didn't include, we didn't, it's fine.
Okay.
This is questionable whether or not you can define most of what we're about to say without the sigma algebra. But I'll have it there just for the sake of completeness. We have some map X that goes from omega cross T into S. Well, S is regarded as the state space. It's the space where our random variable is actually occurring. And I'm saying that for every fixed time, this map needs to be a random variable. Now remember, the definition of random variable is just that this is a measurable map. For each T, the map omega is set to X of omega T is measured. Fair enough? So the way you want to interpret this is to think that this X is a random process when you think of it as a function of omega, but is a process that changes in time when you think of T. So to that end, you define what are called trajectories for fixed omega map T sent to trajectory. So the way you can think of that map is to say, all right, we've picked one outcome. Something has happened in our probability space. And now, as we let T vary from fixing this omega, I think I switched the order of the variables. And we let T vary holding omega fixed, we see the process changing in time. It moves through our state space. We want to keep these two things separate. I want to note a priori, trajectories don't have to be measurable. This sigma algebra that I put in. They don't have to be continuous, they don't have to be measurable. This map T goes to X omega T, in some sense, could behave however bad, in arbitrarily bad. We, of course, are going to want for these kind of maps to behave very nicely, and we're going to give a big emphasis on when they do that. Oh, we're going to have to do a lot of work to get it to continuous. This is going to be when you, for example,
you just defined these two variables. One point-wise, one of the measurable, and another one unmeasurable.
Yeah.
Maybe more.
I mean, in practice, it will always be measurable, and we're going to work hard to get it to be continuous. By definition, all we insist is the map that considers a probability space is measurable, which is to say that it is a random variable. Okay. So we want to next talk about when are stochastic processes equivalent. So when we talked about random variables, there's a couple different ways that we could say that they were equivalent, right? So the primary two ways to see this, though, is that two random variables are considered equivalent if they were almost always equal. That is to say, x, y, equivalent is probability of x equals y. Right? Simple enough. The measure, basically the measure of omega is such that they're not equal to 0. But for stochastic processes, there's actually 3 different definitions that we want to be able to consider. So for stochastic processes, so I'm going to start writing this short one. Now, remember, first I already did this without even setting it up here. When we're doing probability theory, we have a tendency to drop the omegas. So this statement here properly should look like something. This has omega such that x of omega equals y of omega, right? I'm going to have a tendency to drop these. And when we talk about stochastic processes, not only do I drop the omegas, but the t becomes a subscript. These don't work for me. Not only.
Yes, because usually x t means that t is fixed, and then you consider the function of other variable. But here t is there. And only this.
If you really want, I can start. I can write this.
No, you should look. We should have happened. Okay.
So we have several definitions of equivalence. Several, I don't want to say equivalence. I'll say several possibilities. By possibilities, I mean possible ways to argue that these 2 processes are equivalent. The first one is actually equivalent to is a version of the other that didn't say. Every finite protein, T1, T2, Tn, all of which are elements of T. The distribution of x1, xt1, xt2, xtn, and y2, y2, ytn are the same. We say that xt and yt, or the equivalent in this case, are equivalent. And some people will emphasize this by saying in the distribution. Now, let me remind you of the definition of this. Or finite. I'm going to give this exactly the definition. Okay. Because it's not, because I understand that it's not, I haven't made it very clear what this is. I think you could probably piece it together, but let's make it clear what this means. So, what I'm saying is if you pick any finite collection of times, you can consider the set of n random variables xt1, xt2, or xtn. This can be regarded as a random variable where you've taken the n-fold product of the state space with itself. In that setting now, we have a distribution defined by this random variable. So I can say that the log associated to xt1, xt2, xtn of A, so this is a measure in the state space. The n-fold product of the state space is defined as the probability that xt1, xt2, xtn is in N. Is this okay? Is referred to as the distribution. A finite distribution.
And this is you now in S. Or X. Yes.
Yes.
This is you.
a measure, so it's a measure on.
Okay, this is just a push forward of the probability measure to S under this method.
Yes,
Okay,
exactly. So if I pick any finite sequence of times for any stochastic process, I can define this measure on Sn. And I will say the two stochastic processes are equivalent in finite dimensional distribution. I insist that any sequence of times of any finite length, these must all be equal. It's a huge, it's an absurdly large collection of measures. Yes, if every single one of these coincides, then we say that the two processes are equivalent in finite dimensional distribution. This is somehow reminiscent of what it means for two random variables to be equal in law. But the difference, so the word law and distribution here, so that the two get conflated. But yes, this seems a little silly, but I can give you a nice example of this. Nice in the sense that you'll see that what kinds of things can be equivalent in this sense. Dead space over here. So as an example, let's let T, our time space, equal the natural numbers. Let X at time T 1 equal probability to 0 at 1 each. Do I need to say more about this? I think this is sufficient. Okay, so I'm saying let X is a stochastic process such that this is true. That is, that at any given time in the natural numbers, it's either 1 or 0 with probability of 1/2 on a Bernoulli random variable. I'm sure this is, you've seen Bernoulli random variables in some context. Yeah. Now, let's YT find over the same space equal 1 minus X. Think about this. YT is in fact another Bernoulli random variable. It has the exact same distributions, right? Because at every time, it's either 0 or 1, and it's equal to that with probability of 1/2. But it's completely opposite xt. So then xt and yt are equivalent to distribution, whatever, equivalent in this sense here, but they're never equal, or almost. The probability that xt equals yt is 0 for any fixed t.
Okay, we produce the same measure in the larger space, but they are not equal. So that this measures
They're almost surely
all
not
the same points, all the same set.
Exactly. You take for any t, they're almost surely not.
So if it is y for me, then it is y for you. But it's only y.
You can also make this even stranger. You can do things where you take yt and have it equal to this half the time equals something else half the time, and you can introduce a random variable to make this happen. You can make examples arbitrarily strange. The point is that of course there's some meaning to being equivalent in finite dimensional distributions, but it's somehow very weak. This is a very, very weak form of equivalence. What I want to do now is to keep the board nice enough. I've got my definition 1 here. I'm going to go erase this, put definition 2 here, and put it over across, just so in the end, hopefully we wind up with all 3 definitions on the board simultaneously. We'll see. Yes. I try to think a little bit about that. If I was doing this properly, I would have had this not be here and shifted this up. I have 1 definition per column. It would have been beautiful. but not that prepared. All right, so our definition number 2 is actually the one that is the most useful. Most useful in the sense that this is probably the one you really need to focus on. So this for every fixed CUV, the probability that XT equals YT 1. We say that X is a modification of Y. You can also say that Y is a modification of X. I won't prove it because I don't
What
know.
is the difference between the to be equivalent and to be modification?
Right here. These Bernoulli random variables are equivalent in finite dimensional distributions, but they are not modifications of Y. I mean, the probability that they're equal is 0 is as far from this as possible. So what this means is that if you pick any fixed point in time, ask yourself, what is the setup of outcomes such that the two variables are equal? That set must have full measure. And you see right here, actually, this is the this is saying that the example I give you has the exact opposite property. So very much you can have random variables that are equivalent but not modifications.
This thing is all of this. But this function is functions of only for every that is in subgroup. Okay, I'm sorry.
Sorry, I'm not sure.
Okay.
Okay. I do want to say, maybe I give the proof. If two random variables are modifications, they are equivalent. 2 implies 1, but 1 does not imply 2. You can see this by, I'll give the proof very briefly. So suppose that X and Y are modifications. X is a modification, but I don't like the language. But it's how we say it. And in this case, so given some time indexing, the probability that X1, Xn is in some set A, right? Equal probability that X1 and X21 equals Y21, X22 equals Y22, and so on. Xtn equals Ytn. Okay. I can do this because they're independent. The probability of X being in this space, whether it's being equal, these events are independent. So this is equal again. Now I can replace the X's in here for Y's. Y21, Ytn, in A, the same condition, Xt1, Yt1, and so on, which then of course is equal to probability, Yt1, Yt1. As a consequence, this distribution is the same. Notice this is the distribution determined by X. This is the distribution determined by Y. They're equal, thus 2 implies 1.
The new modification one of another is assumed that they are defined on the same order.
Yes, okay, so maybe I should say this. I debated talking about this one. So definition 1, and in fact any definition regarding laws is somehow unique in the sense that two random variables can be equal in distribution or in law while defined on different probability spaces. Absolutely. All of the other definitions we work with will insist that our random variables are defined in the same probability space.
And on the same set.
Yes. Yes. So for this to make sense, they do have to have the same state space. Otherwise, you're not going to be able to define the distribution. But yes, technically, you can have. And it's actually a very interesting question to ask. When you have a random variable defined, can you define another random variable on a different probability space that is equal in distribution? That is an interesting question that crops up. But yes, everything else we do will demand that our random variables are defined in the same probability space. So I will implicit these. I should have said this. I was debating myself. Thank you. Ooh, the class start. Okay. Yes. All right. Now let's talk about our third definition. Our third definition is the strongest. And honestly, I feel like it's somehow the most natural, but in some sense it's too strong. Which is, of course, why we have this. But let's talk about it. So what does this say? This says that if you fix a single time t, that the probability that they're equal will always be 1. But yeah, I'll go with. I have a separate set of notes here. There's 2 equivalent ways to write this. I think I want to do it. So. All right, I'll do this one. Okay. The probability that x of t equals y of t for every t in t. We say x and y in this.
It's just permutation.
The difference here is that for if you fix a time t, and then you look at the values of x and t and y t at that time, the probability they're equal there will always be 1. Here, though, we're saying that they're equal at every single time. So here, in this case, you can imagine that on some countable collection of t's, that they're not equal.
No.
Measure 0, sorry, a collection of oh my god. Thank you. This is just you can have a countable collection of omegas, or you can have a probability measure 0 set where these are not equal.
What you want to say that you can omit the measure 0 set in first case. Why you cannot?
So the first one, think of the first one as like you think of them as points, and the second one you think of them as paths. So the first one, if you look at them as points and where they are, every time you stop t, the probability is 1 that they're on the same. But it doesn't mean that they all got there and that. So most likely many of the paths will be the same, but like you could have some, you have this measure 0 set could be on different kind of paths. But here we're saying that if we draw the entire path of the curve and then take a picture, the probability 1 they're the same. So the first one, we pick our t, we look away, and then we look back at the 2 processes, and then with probability 1, we see that they are the same. In this case, we let them go and start looking all of the time, and with probability 1, they are following.
example?
Yes, let's do that. Absolutely. So a nice example of this to show the distinction. It's a silly example, extremely silly, but it does.
Okay, but if they are continuous with respect to T, it cannot be that, right?
Yes, I agree with that.
The continuity, if you require continuity on T, then these two notions are the same. Is it correct?
But phrases ground motion is not continuous, it's continuous from one.
Yeah. So this is where we get into the thing. We're never going to insist that this is always continuous.
So
It would be too strong. I'm sorry, go ahead.
yeah, but this is like you can modify, right?
Which is
Always is a modification.
So the
Continuous path, right?
yes. So I think this is a reasonable statement that yeah.
I'm sorry, I just took it.
No. It's okay. So let's address continuity just so we get ahead of it a little bit. We're going to define a series of axioms that we want to be true to make Brownian motion to mean which random variable be to give Brownian motion. And it turns out that this will not define it completely uniquely, but we'll be able to show that at least a random variable will exist that satisfies all of these, and you can always modify it so that the paths are continuous with probability 1. What this means to say is that the set of omegas such that the map T to xt of omega is continuous has measure 1. So you can always have a modification that does this, but it would be too strong to insist on some sort of distinction. Let me give this.
Modification essentially on the measure. Functions are constant. But still I don't in this.
Okay, so now I'm going to have time indexed on this interval 0, 1, and our probability space is 0, 1. X. You your function. T. So what I mean by this? What I'm saying is that if omega equals T, this will be 1.
Do you have square? No, I mean, wait. This is the stochastic process. It should be omega and T. So you have square. So the domain of the definition, omega cross T is a square.
Sure, yes.
Okay, great.
Yes, I agree with that, yes. I'm saying let X T be stochastic process. It's 1 if omega equals T and 0 otherwise. Like Y is 0. T. Yeah.
And the radius space, I mean, I guess here it doesn't matter what.
That can be S if you like. Set 0, 1, and E is the powers of S. Okay, so our state space is literally 0, 1, and our the measurable sets are every set is measurable. In this case, X and Y are modifications, but they're not indistinguishable. I think it's immediate that they're not indistinguishable, right? Because for every omega, there's always one point where they're not equal, specifically the T equals omega. Yes? Are we okay with this as that they're not indistinguishable? So X and Y are not indistinguishable, since for every omega 1 X omega equals 1 does not equal 0 equals 1 omega. Right? It's very strange that I can write omega both ways.
Okay, I can really see that they are different.
Yes.
Yes.
So remember, to be indistinguishable, distinguishable, what I'm saying is that you have to find a collection of omegas such that for every time they're equal. But I'm saying no matter what omega you pick, they're never equal for all times. There's always a time when they're not equal. So in fact, the true statement for these two would be that this equals 0. This is as far from indistinguishable as possible. But there are modifications. Choose any time t. The probability that they're equal at that time t is 1.
What is the probability measure you did measure on?
Yes, yeah, Lebesgue measures, yes, or yes, exactly. Lebesgue measures on 0. If you think about it this way, if you pick any fixed time t, the probability that they're equal will be a 1, because the only time the only t with they won't be is omega.
So if you watch this the whole time from 0 to 1, you are absolutely sure that at some point you will see x jump up to 1 and then down. So you're absolutely sure that you will see that the path from x and y are different. But if you just turn on one of the times, then probability 1, x is also 0. And so we won't see this.
If you pick one outcome, omega, if you pick one omega, and compare these two paths, there is a time when they're not equal. No, it's a very subtle difference. But,
Can I just ask,
yes,
is the third definition very useful? Because it seems like
it's
the
very
whole
strong.
point of probability is always to eliminate everything that measures 0. It's
I
my
mean, yeah, you would probably say, and I think we can probably say that if two stochastic processes are indistinguishable, they're the same stochastic process. There's no purpose, there's no way to differentiate them under the theory of stochastic processes. So if you're truly thinking at the level of stochastic analysis, indistinguishable processes are the same thing. But it is too strong. So when we get to this theory of Brownian motion, which is going to be very important to us, you cannot guarantee that the Brownian motion is continuous in some indistinguishable sense. But the statement we will be able to make is that there will always be a modification of Brownian motion that's continuous in T.
The solutions of SDEs are indistinguishable. Like this is uniqueness, right? Of SDEs.
Yeah.
Solution. So in that sense, there.
So maybe this is the better thing to say. It's not that it's a bad definition, it's just that this is as strong as we get. If you know two processes are indistinguishable, from the perspective of stochastic analysis, they're the same thing.
Probability is equal to 1. What does it mean? It means that the measure of omega squared, they have the same value, is equal to 1. But what is the measure, where they are coincide?
The measure where the difference is 0.
Although measure of difference is 0. But
Yeah.
they are all the time different.
So for example, if you pick omega equal to 1/2, then these two will be equal except at time 1/2. And you will going from 0 to 1 will surely pass 1. So they do not have the same time. But if you look at a certain time, then as long as you're not looking at time 1/2, they will be the same. And this is the same for any other omega as well.
This one is the first one. The second one is 0, but the first one is 1. When it's keep looking for
If you're over here, if we're worried about this over here, we pick any time t and ask ourselves, what is the probability that they're not the same? Right, for all of these, the probability that they're not the same is. Okay. Okay, so we have this example, we have these definitions. I will say that there is an equivalent definition to this that is sometimes preferred. I like this definition. I think it's somehow a little bit more accessible, but the definition that some people prefer, the equivalent, like, probability It's 3 over t over 0. SDEs not t 0. So, as an exercise, convince yourself that this is equivalent. Okay. So this is actually the definition we wrote in our notes, and it's preferred in some books. Yes. I will say, maybe this is also relevant. So I think I established 3 implies 2 implies 1. But 2 implies 3 if 2 is countable. So when we're dealing with discrete random variables, as random variables are natural numbers most generally. In fact, indistinguishable and modification are the same. Okay, now let's talk about this. Okay, these are our definitions. This is an interesting, this is often an interesting question to ask, but modification is probably the bread and butter. The most indistinguishable is very powerful. Yes. What time is it? How long am I on? Yeah, let's take a break. We come back and I will explain what a filtration is, and then. So the goal of the next section here is to introduce filtrations, the purpose of filtrations. So.
Because up to now, you define the process of 2 variables, and they have no relation.
Right, yes, absolutely. I agree.
What kind of analysis we can do it.
Okay, so for the probability space, omega f t. We've made certainly a large deal about omega, the set of outcomes. We keep this very abstract generally, except when I do this silly example where it's an interval. But generally, omega is very abstract, right? And p, of course, is our probability measure. But we haven't said much about f. So this is our focus. So remember, this is the analysis parlance, measure theory parlance. This is the measurable sets, which then in probability parlance is the events, or let's say measurable events. What does this mean? This means that this is the collection of sets of outcomes to which we can assign probability, right? So in other words, these are the events.
Outcomes.
Yes, an outcome is a point in omega. Collection of sets of outcomes, and I'll write this again. Outcomes, so omega and omega. To which we can assign probability. So measure theory, is things that we can measure. Probability theory is the things that we know what the probability is. We talked briefly about given a random variable x on this space. One can consider sigma of x is equal to sigma algebra such that x is a measurable. All right, this is a variable. Yeah, so basically what you do is you consider the sigma algebra of the range, pull back by x all of these measurable sets, and consider that collection of sets. We need to measure all of those in order for x to be measurable. And then you ask yourself, what is the smallest sigma algebra that contains all of those? Is this okay? Well, the sigma algebra generated by x.
So this is a measure of omega.
This is a collection of measurable sets.
Yes, sir.
Yes.
So x is the function.
Yes. Yes. X is a
And
function.
this is just,
X is a function, right? So random variable implies that it's supposed to be measurable. Let's just say it's given x.
we want to make it measurable. We define this algebra where x will be measurable. No.
Yes, exactly. Okay. So I have some function from.
And this is the sigma algebra from x.
Yes.
What is this epsilon?
This is a state space with some sigma algebra on it.
Okay.
Yeah, this is a state sigma algebra on it. This doesn't make sense if you don't already have sigma algebra over here. So I'm asking what is the smallest sigma algebra such that x is measurable, which is to say a random variable. Remember, it's all random variable, it's a function that's measurable. What is this really saying though about x? If we have omega sigma x p, what I'm saying is that I have a probability space that precisely is able to measure the random variable x. We can consider this more generally for a stochastic process. So for a stochastic process, we can consider sigma xt, right? Sigma x. How about this? Sigma x. Where what I want find is the smallest sigma algebra such that for every t in t, sigma xt is measurable. Another way to say this, maybe a little bit more symbolically, sigma of x is the smallest sigma algebra containing the union across T and T of the sigma xt's. This statement makes sense. For each fixed T, xt is a random variable. So sigma xt is defined over here. I take the union of all of them, and then I say what's the smallest sigma algebra containing all of those. So I can do this. This is a reasonable way to insist that we have some of the smallest sigma algebra on our probability space that can measure xt for all t. And it works, and this is all well defined, but it's somehow too coarse. What I mean by this is that or too fine, depending on what you want to think about it. But somehow this structure, this sigma of x, is not appreciative of how x changes with time. So, right, sir. We can add more structure to this to appreciate that. Suppose that it's going to have to do for a really fancy f, because I'm not sure if it is better than this. So f is equal to
where FT is a algebra omega.
Okay. We have this. And S being within all S. So what am I doing here? I'm saying that now not only do we have a single sigma algebra on our probability space omega, but in fact I have an entire collection of sigma algebras indexed by time. So for every time ft is a sigma algebra, and moreover, as time goes forward, the sigma algebra can only grow.
And now it's sigma algebra does not depend on linear variable.
No. So this is an example of somehow if I have a random or a stochastic process, this is the smallest one. It would make sense.
It's just,
But let's say just all of
it's
this.
just for the set of sigma algebra.
So at this level, we don't even need a random variable stochastic process of n equals. Then f is called a filtration. Actually, let me add one more condition to insist for making the filtration. So let's say we've got this probability space. We've got that collection of sigma algebras. If F equals the intersection of T equal T and T of T. That's no annotation, it's going to be bad. There we go. Yeah, I'll leave this one on the straight as well. So, be clear about what this condition says before I give it a name. Filtration. I have now a collection of sigma algebras for every time t. This is this very strange app to indicate the whole collection of them. Whenever time increases, the sigma algebra can only get larger. And moreover, if you take the intersection of all of these, you actually recover the sigma algebra that we had in the space to begin with.
So this is the smallest sigma algebra in this point.
Well, they're growing, so their intersections really, this is really just a limit. Yeah. But yes. F, by this double curl, I mean the whole family, is called a filtration. F.
And this parameter,
Sorry?
you can see. So not necessarily that from 0 to infinity, whatever.
No, so remember, so T can be any index set that we want for our stochastic process, but it's almost always going to be the natural numbers or the non-negative groups. Sometimes an interval from 0 to something.
People do not go beyond the positive marks. Yeah, great. It's just,
So we have some notion of a filtration. Yes.
When you define the F as the intersection of the FTs, since the FTs are always growing, isn't that the same as F0?
No, F infinity.
Yeah, this is why I was wondering.
Uh,
Do you have the intersection here?
Oh my goodness. Yeah, this is terrible. What am I doing?
What? Okay.
I'm sorry. Yes, absolutely. I'm losing my mind. It's absolutely, it's not supposed to be F0, it's supposed to be F infinity, which of course means the union. In general,
Wait, no, filtration is more like we integrate from T in 0 capital T and we index it on capital T. It's more like a list of sigma algebras that grow. You know, what else is the infinite prime sigma algebra?
yeah, the F infinity.
And this is not the filtration. You have to write a sequence of all the sigma algebras.
You're thinking about filtration adapted to a stochastic process, which I'm getting to next.
Sorry.
You're thinking of the filtration associated to a stochastic process.
Yeah.
That's what I'm getting to next.
Okay.
This is an abstract filtration. This is an object that can exist on this space, even if we have not chosen a random or a stochastic process.
All right.
So I'm just saying, all I'm saying here is that we have a collection of sigma algebras indexed by time that grows. And if you took the union of all of these and went all the way to infinity, you would eventually recover the sigma algebra that we have every in our space. This is all I'm insisting for now. So now I want to go back and see how to relate this concept to this. Because if I took ft to just be sigma of x and I divide them here the whole time, yes, this would be a filtration, it'd be a very trivial boring one that would just always this. What I want to do now is make it so that the filtration somehow adequately understands the changes in our stochastic process. Does this make sense? Okay. So
You need a sigma algebra because it's for growth. So if you pick two sets, you know it's going to be large enough that it makes both of them.
So given our probability let me write this last thing, and I think it will become clear. I think your definition will agree, and then the intuition will make a lot more sense. And this and a stochastic process X. So what I mean by this now is that this, for every t, is measurable, right? We've insisted on this in the definition of a stochastic process. Define f t to be equal to sigma x. What is this? Second, that at time t, consider the single random variable. Yes?
Okay, good.
At time t, consider the single random variable xt. You can generate a sigma algebra. This is the smallest sigma algebra that can measure xt. Of course, ft is a sigma algebra, but we don't necessarily have this condition, right? So what we do then, it's a different name to make that better. We want to take the
Just write small excess.
and do we see the difficulty of the definition I was writing down at first? No, let me write it so that I can explain the error. Okay. If I did this, this is interesting because for every time t, this is a sigma algebra.
You
But-
and this x, you just absorb that single point or something like that, and you get something.
Exactly. Yeah. This isn't a filtration. Because S not necessarily is ft or S less than t. We don't know this on both. It's not clear. So instead, don't take this. Fine. X would be the smallest sigma algebra containing xs for all s less than t. So this notation is meant to say that if you consider x at any time s before t, it must be sigma measurable. Then
Essentially, this is the perception of sigma algebra related by x. X or any s.
yes, this is called the filtration adapted to x.
each process produces filtration. The filtration depends on the definition of the stochastic process. It's not by filtration. Filtration.
Okay. So why do we care about this? Why am I spending all this energy on this?
The only problem I have with your statement here now is that I cannot see that you could automatically guarantee that you get the whole of F by doing this.
So what I really need to take, right, is
Yeah, that's all.
remember I gave the definition that sigma of x is the smallest sigma algebra that contains all of x. Yeah. So if I want this, I really should put that. Yes. Okay. Now let's now that we have a definition set for what is a filtration, just arbitrarily some collection of sigma algebras that do this, and a filtration adapted to a process is the smallest filtration, such that at each time it properly measures the random variable and everything the random variable done beforehand. So what you do now, how you interpret this. So is say that T contains all of the events that are knowable at time T as
Sometimes the sentence over time limits.
respect to xt. So what I'm trying to say by this is that at time t, the stochastic process xt has done something, it's moved around, it's existed in our state space in some sense. Ft precisely consists of the events that we should know as determined by the process xt up to time t.
Exactly. So f of t, this is a collection of measurable sets where x will be x of t will be measurable for t. Yeah. For any s before t.
So you can ask yourself if
You can measure.
you can measure events that should be determined by that
Yeah,
time.
associate probability for any xs when s less than t.
So I can ask myself, for example, let's say if the state space is Rd, I can ask myself, has X left a ball radius R by time t? That would be Ft measurable. Because at time t, you should know whether or not xt has left this ball. But if I give you a second time, let's say R, S, and S is greater than t, the probability that xs has left the ball at time s should not be Ft measurable. Does it make sense? So I can say that ST greater than R for some S less than T. All right. AT is certainly in. If L is greater than T, and L is not necessarily in. This is the kind of thing we're trying to get at with the filtration. I say not necessarily, because it could be, depending on the nature of your stochastic process and other things going on. But a priori, it's not clear.
Now the option is very huge measure.
Yeah, I'm saying x t omega takes place in Rd, we're on a measure on. Right, I'm just giving a very specific example. We're talking about a process that lives in Rd, and I want to know, does the process leave a ball radius R? That's all. It is a very specific. Right. Wish the signal would be, does not want to do that. I think we should. Yeah, we can talk about, maybe not, we don't bother. Sure. So generally speaking, when we're working with stochastic processes, we want to have adapted stochastic processes, right? Because we want to be able to talk about sigma algebra that measures precisely what x has done up to that point in time. We can also give some definitions of measurable and progressively measurable. So, x measurable. How diversity. Probability space, our time index space, and our state space. Measurable with respect to product measure. Something like this, right? So if it's measurable with respect to this product, to the product measure, which is uniquely defined because we're assessing everything in sigma finite, then sure, it's measurable. Given also filtration and adapted filtration exists. We define T the T's right. So TT is going to be all of the times up to time T. Fine. And I'll say that how T progressively measurable. If okay. What's the point of this? I want to make sense of what it should mean for a random variable to be measurable. Here, I'm saying if you pick any fixed time t, do this. X is measurable with respect to these products of algebra. We call it measurable. That's not a surprise. I'll say it's progressively measurable when I have a filtration. And then for every time t, I consider the times up to t. Intersect this with the sigma algebra on our time index space and say that we should be measurable with respect to that.
Okay, T for you, okay, if T is just, for example, 0, 1 interval. So what is what is the difference between T tail and curl?
So curly T is the sigma algebra. It's measurable
Yes,
set
okay,
of
this is
time.
sigma algebra, and
This is just
sigma
times
algebra.
from 0 to 2. Okay. I mean, it's different if it's countable or something. But then what I'm saying is take this, the measurable sets in t and restrict it so that we're less than time little t. If we can measure x with respect to this, then it is progressively measurable. And the only point of this is to say that somehow the filtration properly respects the measure on time index. Because this is exactly the question we're asking. Remember, a priori, random variables or only measurable for fixed t with respect to omega. I'm saying these are a definition of measurable so that in both variables and measurable it respects time filtration. All right, the last thing I'll torture you with in this direction is stopping times. Use this. We actually want. So stopping time is a specific type of random variable. It turns out to be incredibly useful if, I don't know, very slightly technical. Yeah, I guess I did mention. Everything I said about completion is necessary. So I said this in the very first week. We assume that everything is complete. That is, in any of these sigma algebras, if you have any set of measure zero, all subsets of it are measurable and have measure zero. This is definition that I wanted. Yeah. Right. Okay. So given our probability space and filtration, notice that I'm not insisting this is any sort of adaptive filtration, although almost always is. A random variable tau, little tau, it goes from omega into t. Which is called a stopping time. Yeah. If the event tau is less than t, that's a measure. So what on earth is going on here? The intuition is that tau should tell us when something happens, when some event occurs. For example, leaving a ball for the first time, or getting into a certain point in space, or when two things collide. We want to have a measure for when does something happen. So the notion is that given some outcome omega, we should be able to understand when does this event we care about understanding occur, when does it first happen. And then tau of that omega should be what time does it happen. That's the notion. So to make this precise, what I say is that the event tau is less than some t. So in other words, a thing happens before time t should always be knowable by ft. You can see it. So you can see it as being.
It's inside of it.
Yeah, exactly. It's inside of it. All I'm saying is that I want to know. I have some variable tau that tells me, given some outcome, there's a certain time when something's supposed to happen. That should always be knowable by that time. Does this make sense? This is a stopping time. This turns out to be really useful for a lot of purposes. For example, in the theory of SDEs, we have problems with blow-up times. And in order to avoid this, we can determine our random variable that tells us when does this blow up, and then insist that we stop our random variable before that. So what we'll do often is, given a stochastic process X, we will define y t be equal to x wedge half. So what's going on here? I'm saying that.
Is it minimal?
Yes, yeah. So this is just an notation. So what does this do? This says that before tau, y of t and x of t are the same. After tau, y t stays fixed at y tau.
So now you find not random variable.
It is a random variable. So yeah, that's the. So here's the trick of it. If we knew deterministically, let's say we have this process and we know at time 3 seconds, the process leaves the ball.
Where is the variable? So this is just in terms of the, so here I can calculate all these omegas where tau of omega less than t3. And here in this, right, so y of t is equal to x of t for all omega where tau of omega bigger than t. Yes?
Yes.
So the first line is just the set.
Mhm.
On this set of omega, so they coincide on the set of omega where this tau of omega bigger than t.
So the easy way to see it is pretend for a second this wasn't a random variable. I want y of t to be equal to x of t up to time 3. I don't know. Up till time 3, they're equal. And then after time 3, xt is or yt is fixed at whatever happened at time 3. It stops at that point. The only difference between this, my writing over this in blue, and what actually happens, is the fact that the stopping time itself is random. That is, you don't know ahead of time, so you've chosen an outcome omega when it stops. But it does the same thing. Y of t will match x of t until whenever this stopping occurs, and then it stops. So we call y of t a stopped process.
I don't understand. And x tau became the constant.
Yes. So whatever time tau is, whenever the process is supposed to stop, whenever tau is, y will be fixed in a constant at that time x tau. At the value x tau. It'll stop there and won't change. So maybe the visualization of this. This is our time. These are states things, right? So let's pretend R and R. So X is this, right? This is X2.
The constant is x of tau. The random process,
Okay, to give you this picture, we'll as time goes on, we've got a random process xt that does, oscillates. It does whatever xt does. Then for some given omega, tau turns out to be right here. What will happen is that y will match until this time here and then stay constant.
that constant is equal to the value of the
X. This is the end. But the point is that this is made more interesting by the fact that we don't know where tau occurs up further, because tau itself is a random variable. So this can occur in different points, happen at a different time, depending on the outcome. This is all right. The big claim I want to make, the thing that I think is important, is adapted to X. So it is a stopped version. we have a stopping time tau, and we have an adapted random variable x. If we stop x using the stopping time tau, YT is also adapted to the change. This is the point. Because we're going to have a whole bunch of random variables that we're going to care about measuring with respect to ft. And we want to understand that we think this is the definition for a stopping time, that we don't lose any information about measurability. Pretty bad. Okay. I don't know. Do I talk briefly about conditional expectation?
No,
Yeah.
but you could just give a little more because
Sure. I'll give you a technical condition that we're just not going to prove that will answer this question about continuous modifications. Okay. Criterion Colmar, which is somehow essential in the construction of Brownian motion. Yes. It's actually two. I want to this time. Okay. All right. So let X be a stochastic process. There exists C and epsilon greater than 0, delta greater than 1, and that for all S and C time variables, yes, the expected value xt minus xs delta. So this is of course an absolute value being taken in here. So we have to add this as a is less than or equal to E minus s plus epsilon. This is a continuity criterion, right? Then for all alpha the capital interval 0 to epsilon over delta. There exists a continuous modification of x. Well, I can say very clearly what I mean by that. Such that the trajectories next to YT are what's going on here? I've got a stochastic process living, huh? Yeah. All right, I've got a stochastic process. When our state space, which is RD, it's RD with the Borel limit and the absolute value. You know, if we can find some constants, such that we get this sort of criteria that expectation.
RD, this is the normal RD.
Yes.
Thinking about delta.
Yes. This is the normal. The point is that we can control the integral of the probability states of delta by just the normal length. The normal in this sort of condition, what we're saying is that we can guarantee that the trajectories of a modification are alpha Holder.
And this is 4 divided by delta.
That's epsilon divided by delta.
Okay, I'm sorry.
No, that's just my hand there. So our epsilon over here, and our delta. So the point of this is that if we're able to find a stochastic process, find it any way you want, that satisfies this sort of criteria, it's not guaranteed that X itself is continuous or that its trajectories are polar in some nice sense. But what we can do is find a modification. And remember, this means that for any fixed t, the probability that xt and yt are equal is 1. But they're not necessarily equal for the whole trajectory. This is the distinction between these two forms of equivalence. We can have a modification such that the trajectories are opposite. And this is what we're going to do when we construct rounding motion. Rounding motion is going to be some reasonable, logical set of axioms that you say, okay, yeah, if we have random motion, we want it to satisfy this. And the very final beautiful step will be to see that any stochastic process we construct satisfying those axioms will satisfy this, so we can make a modification that gives us continuous trajectories.
Some ideas of the roof, like from the losing theory or something. Do you know what?
I've seen this. Do you give an answer? 'Cause I've seen this done with a long time ago. It was rather technical.
It's what you have to do is take for interval, let's say it's finite or t, and then you make the position of it. And then there's a bunch of little local stuff that you generalize, and at the end you promise that you have to have alpha under, not begin with this, begin with something weaker. And for this, you then use equivalent quantity around to all Schwartz.
Okay, the first you probably want to show that this is continuous. And then alpha further is something much more great. But to make it continuous, do you remember losing things? Okay, if it doesn't agree, it doesn't matter.
Yeah, we can go.
No, if you can avoid it, you got it.
I don't think we want to do this in the seminar because it would take an entire second day.
Yeah.
I remember it being extra. You know, the one I'm remembering it was very constructive. There might be a not constructive way. It's easier. I don't know.
I think we'll just focus on increasing.
Yeah, because it's not that exciting. It's not. I've always thought this is not that surprising. This looks like a continuity criterion. So I feel like it's not surprising when you get a result of that sort that you should be able to make things continue. I don't know. All right, I will leave us there. We now, I think, have